So now we will try to solve this question number 13. And in this question we are given that we have two charges of equal mass but opposite polarity. So let us say I have plus q and minus q charge, and the mass of these both two charges is equal to m. And when they are placed 2d distance apart, due to the Coulomb force of attraction, they move towards each other. And it is given that when the distance reduces to d, the speed of each particle becomes u. And we have to evaluate what is the distance at which the particle speeds become 2u. So electrostatic force is given by minus kq squared upon r squared, and this is a conservative force. So in case of conservative force, if I take 2 point A and B and I have to calculate the work done to take a particle from point A to B, in every case, if I go from this path, from path 1, path 2 or path 3, in all these three cases the work done by the particle from moving from point A to B will be same, because in case of conservative force the work done is path independent. So in case of conservative force, if the work done is path independent, then initial energy is equal to the final energy, because there is no external force that can cause unconservation of energy. So I will use conservation of energy theorem to solve this problem. And in case of charges, the potential is given by kq squared by r. So initially it is given that the two charges plus q and minus q are 2d distance apart. So when they are 2d distance apart, I can write minus kq squared by 2d is the energy initial. And when they are at a distance d, the velocity of each particle is now u. So this particle and this particle at a distance d have velocity equal to u. So energy final is equal to minus kq squared upon d plus half mu u squared. So what is mu? Mu is the reduced mass of the system. Reduced mass. So reduced mass is given by m1 into m2 upon m1 plus m2 for general 2 mass, but in our case it will be m by 2, and mass of the particle is unknown, so indirectly we have to find reduced mass too if we don't know m. So let us now equate energy initial and energy final. I will get minus kq squared upon 2d is equal to kq squared upon minus kq squared upon d plus half mu u squared. Taking this term to the right, I will get kq squared upon 2d is equal to half mu u squared. So now we are asked what will be the distance of the particle when the speed of each particle is 2u. So let us say from this initial configuration, particle come to a new configuration at a general distance r, where the speed of each particle is now 2u. So in this case, energy initial will be equal to minus kq squared upon 2d. But energy final will be minus kq squared upon r, because this is an unknown quantity that we have to find, and at the distance r, the speed of each particle is now 2u. So half mu 4u squared. So velocity is now 2u, so v squared is equal to now 4u squared. So if I now equate these two equations, I'll get minus kq squared upon 2d is equal to minus kq squared upon r plus half mu u squared into 4. So I can substitute the value of mu squared from over here. So I'll get minus kq squared upon 2d minus kq squared upon r plus kq squared upon 2d into 4. So this will cancel out and I will cancel out qq squared and I'll get 1 by r is equal to 2 by d plus 1 by 2d. If I now evaluate it, it will be 1 by d 5 by 2. So r is now equal to 2d by 5. So this matches option D. So this is our correct answer. So we see how we can use conservation of energy theorem in case of conservative force. So conservative force are the force in which the work done by the particle from moving to any 2 point is independent of its path. So let us say if I have 2 point A and B, if I go from this path or from this path or from this path, any path, but the work done will be independent of the path taken. It will be dependent on the position of the 2 points. So let us now solve more problems and see how to do problems and how to approach a problem. Let us now discuss problem number 15, in which we have to evaluate the equation of motion of the block of this two spring mass system. And if the block is displaced by a displacement x, then we have to evaluate the equation of motion of this system. So I'll discuss two methods to solve this problem. The first is Newton laws of motion, in which we have to just draw the force body diagram and evaluate the equation of motion. And in the another method, I will try how to write the potential energy of this system when the mass is displaced by a displacement x. So let us discuss. So initially, when the system is undisturbed, that is, if the mass was not displaced, then the spring 1 will be neither compressed or not extended. Similarly, for spring 2, it will not be extended nor compressed if the system is undisturbed. That is, when it is not displaced by a displacement x. As soon as we displace this mass by a displacement x, then the spring 1 will extend by a distance x. So the spring will extend by a displacement x, and similarly in the spring 2, when we displace this mass, this spring 2 will compress by a distance x. So let us now discuss the force body diagram method. So suppose this is our mass, and when I displace the block by a displacement x, then the spring 1 will try to bring it back to its original position by applying a restoring force, which is given by minus kx. Similarly, spring 2, which is compressed, it will also try to move or push the block to its original position towards the left. So the restoring force from the second spring is also minus kx for the second spring, and this is for the first spring. So I can write F is equal to minus kx, which is equal to F is equal to minus 2kx. So F will be the conventional definition of this block, which is related to the acceleration of the block. So F is equal to mx double dot, and this will be equal to minus 2kx. Then I can bring the mass to this side, and I can write x dot plus 2k by m, x is equal to 0. This is our equation of motion if we draw the force body diagram for the system. Now the another method that we will discuss is based on the potential energy of the system. So if I compress the string, then it is, if I displace this system by a displacement x, then the spring 1 will be extended by x, and the spring 2 will be compressed by x. So the potential energy of the system will be half kx square. This is for spring 1, and similarly for another string that is compressed by x, I can write half kx square for spring 2. This is our spring 1 and this is our spring 2. If I displace the mass by x, then spring 2 will compress and spring 1 will be extended. Okay, so if I just add up these two quantity, I will get kx square. And for a conservative force, that is which is in which the work is path independent, I can write force is equal to minus dv by dx. So if I substitute the value of potential kx square over here, so I'll get is equal to minus 2kx, and using the definition of force is equal to mass into acceleration for the block, I can write this. So x double dot into m is equal to minus 2kx, and if I just take mass to this side, I'll get x double dot is equal to minus 2k by m x, and if I take this term to the left side, I'll get the same answer. So we see that how we can evaluate or solve this question by using two methods. So this completes our discussion on the question number 15. So let us now solve more problems on the topic of on this topic, that is Newton laws of motion and Newtonian mechanics. So in question number 17, we are given that we have a three spring and a mass system, and the configuration of the system is kind of like is this. So we are asked that if I displace the third spring by a displacement x, then what will be the equation of motion? So this is the configuration of the system. We have spring number 1 and spring number 2 aligned at 90 degree, and from one of the corners or the vertex of the mass, we have spring number 3 that is attached to the wall at an angle of 45 degree from the horizontal. So let us now solve this question. To understand this question better, I will take another picture that will help you understand how when we displace the spring, how is the configuration changing. So suppose that I align my diagram like this. Okay, so if I now, so this is my diagram, and suppose that I I move the block of mass m toward the spring 3 that is vertically downward, then let us say this is the initial configuration of the spring, and the final point at which the mass is now is this, that is at a distance x from the initial position. So from this point, if I compress the spring in this direction by a displacement x, then the final position of the block will be this. Okay, so the spring will be compressed, the spring number 3 will be compressed, and what will happen to the other two strings? The other two springs will extend. Okay, so the other two springs will be extend. The spring number 1 and spring number 2 will be extended. Spring number 1 and spring number 2 will be extended, and spring number 3 will be compressed if I displace the mass along the vertically downward direction. So let us suppose that if this is the x is the distance by which the spring 3 is compressed, then if then this angle is 45 degree and this angle is 45 degree. So if this angle is 45 degree, then if the spring number 3 is displaced by x, then if spring number 3 is displaced or compressed by distance x, then spring number 2 and spring number 1 are extended by, I can calculate the extension. This is the extension and this is also the extension. That is, when I compress the spring number 3 by a distance x, this is the distance x by which the spring is compressed, and this is the final position of the mass m. And if this is the distance by which the spring number 3 is compressed, then this direction, this represent the extension of the spring number 1 and spring number 2. So x cos 45 degree represent the extension of spring number 1, and x cos 45 degree represent the extension of spring number 2, and the compression of spring number 3 is x. So spring 1, that is this spring, is extended by a distance of x cos 45 degree, where I have used the simple trigonometry to calculate the projection of x along this direction. So spring number 1 is extended by x cos 45 degree if spring number 3 is compressed in the downward direction by x. Similarly, spring number 2 is extended by, that is this spring, when it is extended because spring number 3 is compressed in the vertically downward direction by x, then spring number 2 will be extended by x cos 45 degree. This is extension and this is also extension. And similarly, spring number 3 is x, it is compressed in the vertical direction. So now let us say this is the initial configuration, this is the configuration of the system, and when the spring is compressed by a distance x and spring number 1 and spring number 2 are extended, then the mass or the spring will try to align itself to its natural position or its natural length. So when the system regain its original length, then the restoring force will act in this direction due to spring number 1, and due to spring number 2 the restoring force will act in this direction, and due to spring number 3 the restoring force will act in this direction. Let us consider each spring separately now. So if spring number 3 is compressed in the vertically downward direction, then a restoring force will try to align the spring to its natural length. So if spring number 3 is compressed, then it will shoot back in the upward direction, and that force is F3. This is the restoring force by the spring number 3, and the value of the restoring force is minus kx. Similarly, spring number 2 when extended by a distance of x cos 45 degree, because this is extended, this is also extended. So when spring number 1 is or 1 or 2 is extended by x cos 45 degree, because because spring number 3 is compressed in the downward direction, then F2, when the spring is extended or when it is moved down, like in this figure, it will try to shoot back to its natural position, that is in the upward direction, and this is the restoring force by spring number 2, which is equal to minus k x cos 45 degree. Similarly, over here in the spring number 1, the restoring force will be minus kx cos 45 degree, because when I stretch the spring number 3 downward, the spring number 1 will be extended and it will try to regain its natural length by pushing the mass upward. So this will be the direction of all the three forces. So now I can resolve these two forces. So let us say if I resolve, this is vertical and this is 45 degree and this is also 45 degree, and this is minus kx cos 45, and this is the horizontal component of f1 and f2 will be cancel out, because the f1 parallel f1 parallel is this. F1 parallel will be equal to minus kx by root 2. Cos 45 value is root 2, and if this angle is 45, this is 45 too, then this is also 1 by root 2. So this value will be equal to kx by 2. Similarly, f2 parallel will be equal to minus kx by root 2, 1 by root 2, which is equal to minus kx by 2. Since both these forces are equally and opposite, these parallel forces will cancel out. Now we have to see the perpendicular component of the f1 and f2, and the perpendicular component of these two forces will be in this direction. F1 perpendicular and F2 perpendicular will be in this direction. So F3, F1 perpendicular and F2 perpendicular has the same direction. So what I can do is write mx double dot is equal to minus kx minus kx by root 2 sine 45. This is also root 2, and over here again, due to spring number 2, which is equal to minus kx root 2 and 1 by root 2, and I'll get minus kx minus kx by half minus kx by half, which will add up to minus kx. So the final answer will be minus 2kax. So mx double dot plus 2k by x is equal to 0, and if I divide by mass on the both side, I will get x double dot plus 2k by m x equal to 0. So this is the equation of motion for this configuration. So the final answer is x double dot plus 2k by m x equal to 0. So this is our final answer. So I will repeat the solution once again. So if I displace the spring number 3, the spring number 3 in the downward direction by a distance x, then spring number 2 and spring number 1 will be extended like this. So if I displace spring number 3 downwards, the spring number 3 will be compressed and spring number 2 and 1 will be extended. So if it is displaced by a vertical distance x, then by using the trigonometry, I can calculate the extension in along the spring 1 and spring 2. So along the spring number 1, the due to the trigonometry, this will be x cos 45 degree. That is, spring number 1 will be extended by x cos 45. Similarly, spring number 2 will be extended by x cos 45 degree, and spring 3 is compressed by x. Okay, so if this all these three forces will act like this in this way, and the parallel component of the f2 and f1 will cancel out, and f3, f1 perpendicular and f2 perpendicular all apply in the same direction. And we can also see this from the figure, that if I compress the spring along the vertical downward direction by x, then the spring number 3 will shoot upward, will try to shoot the particle of box of mass m upward, and spring 2 will again try to push the mass upward, and spring 1 number 1 will also try to move the mass in the upward direction. So this is how we have resolved our forces, and we have just calculated the final equation by adding up all the perpendicular. This is due to spring number 3. This is the f1 perpendicular component, and this is also the f2 perpendicular component, and I have added up these three forces, and this is my final equation of motion. Okay, so this finishes our discussion on question number 17, and we will move forward to another question. So let us now solve question number 19. We are given that we have a string, and from this string, at the end of the string, we have a mass, we have a block of mass m that is hanged at the end of the string, and let us say I elongate this string by some distance y, then I have to find out the equation of motion for this string. So let us say when the string is extended to to a vertical distance y, at that instant at that instant the block experiences a force mg and a minus ky on the upward side. So this is the restoring force. So if the body is extended to a new point y by a vertical displacement y, then the block of mass m will experience a force of mg, that is the weight of the body, and minus ky due to the restoring force, that the spring will try to push it back to its natural length. So at that instant I can write m y double dot is equal to minus mg plus ky. If I take downward direction to be negative, then this is the equation that I can formulate, and if I divide it by m on the both side, I will get minus g plus k by m y. So by taking this y double dot plus g minus k by m y is equal to 0, or y double dot minus k by m into y plus g equal to 0 is our equation of motion for a string that was elongated horizontally. So this is our equation of motion for a string that was elongated vertically by a distance y. So again I repeat, to solve this question we just elongated this string to a distance y from its natural length, and at this point the force experienced by the particle is in minus ky, that is the restoring force, that is plus ky, the restoring force, and mg, that is the weight of the body. And if I just formulate the Newton laws of motion, that is if I balance the force, this is the equation that I will get, and this will be our answer. So this completes our question number 19. So let us now solve this question number 20. So up until now we have solved a lot of questions, and to approach a question we have to just read the question and just target to the point where the question asks what we have to calculate, and we have to just formulate an approach and see what all do we know about the question, what are the concept that we can use, and then we can just calculate what is asked in the question. So in the question number 20 we are asked that we are given two particles of masses m1 and m2, and they are placed d distance apart. So consider this is our particle m1 and m2, and they are put d distance apart, but due to the gravitational interaction between these two bodies, they will approach each other, and because the gravitational force of attraction is given by proportional to 1 by r square and in proportional by m1 and m2, force due to gravity is given by the Newton laws of gravitation, and due to this Newton law, the two masses will attract each other with this force, which is given by g m1 into m2 by r square. So the particle m1 and m2 will be attracted to each other by this force g into m1 into m2 by r square, and when they are approaching towards each other, let us say they approach each other with a velocity, that is v approach. This is the velocity of the approach, and the reduced mass for this system will be mu1, that the mu reduced mass will be equal to m1 into m2 upon m1 plus m2. This is the reduced mass of the system. So if two bodies that are kept d distance apart, and if they are attracting each other via gravitational attraction, then they will move towards each other with the velocity, that is their reduced mass will approach each other with a common velocity v approach. So let us now formulate equation to derive what will be the velocity at an instant when the distance between the particle is equal to d by 2. So when the particle m1 and m2 are d by 2 distance apart, we have to calculate what is the common velocity of approach. So let us first say I have two particles that are d distance apart, m1 and m2 are d distance apart, then the potential energy of the system is given by minus g m1 into m2 by d. Okay, so when the particle m1 and m2 are d by 2 distance apart, and this is also equal to the total initial energy. This is the total initial energy, which is equal to the potential of the particle mass 1 and m2 d distance apart. And when the particle are d by 2 distance apart, then the potential energy is given by minus g m1 into m2 upon d by 2 plus half mu v square. So these two particles will approach each other with a common velocity of approach. So this is equal to energy final. So since our system is conservative, that is the force that is present in the system is gravitational, and gravitational is a central force and it is a conservative force. And for a conservative force, we know that the work done is path independent. That is, if I have to move a particle from A to B, then the work done by this path, by this path, or this path will all be equal because the force is conservative. So if our gravitation is present and if the force is conservative, then it doesn't really matter what path we take. The force will, the work done will by the particle will be path independent. That is from point A to B, the work done by the particle will be equal for all these paths taken because the work done point depend on the depend on where the point A and B are situated. It really doesn't depend on the path taken by the particle. So if the force is conservative, I can equate energy initial is equal to energy final. So my equation will be minus g m1 into m2 upon d is equal to minus g m1 into m2 upon d into 2 plus half mu v approach square. So if I take my this expression to this side, I'll get g m1 into m2 upon d, which is equal to 2 mu v approach square, and the value of my mu is equal to m1 into m2 upon m1 plus m2. So by substituting the value of this expression over here, I will get 2 g m1 m2 upon d is equal to m1 into m2 upon m1 plus m2 into v approach square. Then these two quantities will cancel out and v approach will be equal to 2g by d into m1 plus m2 under root. So this will be our final answer for question number 20. So now let's solve the next question. So let us now try to solve this question, and we are given that we have a block of mass 5 kg and we have to lift this mass with the help of a rope, and we are given that the maximum tension that the rope can bear is 100 newton, and we have to evaluate what is the maximum possible acceleration of the block given that the maximum tension that the rope can bear is 100 newton. So suppose this is our rope, and at the end of the rope we have a mass of 5 kg that we have to lift with the help of this rope, and we are given that 100 newton is the maximum tension of this rope. So let us now first draw the force body diagram of this mass of 5 kg, block of mass 5 kg. So weight is in the downward direction and tension is in the upward direction. So if I assume that if the block is moving downward, I can write Wg minus T is equal to Ma if the block is moving in the downward direction. So the weight of the block is m into g, which is equal to 50, because 5 into 10, where 10 is the acceleration due to gravity g, and the tension is minus 100 newton, which is equal to 5a. So acceleration is equal to is equal to minus 10 meter per second square. So the negative sign represent that the block is moving in the upward direction, because initially we have assumed that the positive direction of the acceleration was downward. So the negative direction is in the upward direction. So this negative sign represent that because we have initially taken the block to be moving downward, but after solving the question we see that the acceleration is negative, so that means the block is moving upward. So this is our acceleration of the block. So we see how we can draw simple FBDs, and that is force body diagrams, and write the equation and balance some forces, and can evaluate the missing quantities like acceleration in this question. So let us now do more question on the basis of Newton laws of motion and Newton's second law, and try to find out how do we solve problems